So first of all, there's the definition of what a differential is. And it says let y equal f of x represent a function that is differentiable on an open interval containing x. The differential of x is denoted by dx, and that's pretty important. And it's any non-zero real number. The differential of y is denoted by dy, and that's what it's defined as being. dy equals f prime of x dx. Now this is not a difficult concept. This is stuff we've already been doing. We're just putting a new name to it. And so first of all, it says let y equal x squared. Find dy when x equals 1 and dx equals 0.01. So that's the first thing I'm going to find. So I know if I have the original function y equals x squared. What I'm going to do now is I'm going to find the derivative of y. And so if you remember, once upon a time when I did this, I could write this as y prime. That was one way. Another way, if you remember, was to write it this way, dy over dx. And so what would the derivative of x squared be? 2x. There you go. So now, if you notice the problem, they ask us to find dy. Okay, so what I'm going to do now is I'm going to isolate dy and make it all by itself. So I really end up getting then dy to equal 2x times dx. So it says find dy when x equals 1. So I'm going to take 1, plug it in for x, and when dx equals 0.01. So all I have to do is plug those values in. So I have 2 times 1 times 0.01, which is what? 0.02. And so that is what dy is defined as being. So see, essentially, this is something we've already done. We're just finding the derivative, but we're saying we're finding the differential. And so notice it says now compare this value with delta y for x equals 1 and delta x equals 0.01. So now real quick, okay, delta y. Change in y. You need to make sure you get this down. Delta y will equal the following. Okay? F of x plus delta x minus f of x. That is basically the change in y. So now what I'm going to do is plug in what I know. So this is that delta y is kind of important, especially on your homework. So make sure that you get that down. So let's plug in what we know. Okay, we know, all right, that in this case they want x to equal 1, so I've got 1. I know that delta x equals 0.01, so 0.01 minus f of 1. So I'm going to go ahead and add the parentheses together. And so basically I get f of 1.01 minus f of 1. And so now what I'm going to do is I'm going to go ahead and basically plug 1.01 into my original equation. Okay? And I'm going to plug 1 into my original equation. My original equation here, y equals x squared. So that ends up giving me 1.01 squared minus 1 squared. So whatever your original equation is, that's what you're going to plug it into. What is 1.01 squared? And I know that 1 squared is 1. So if I subtract the 2, I really get 0.0201, and that's going to equal your delta y. So compare the two. They're close. Okay, not quite the same. Now, the biggest thing that we're going to find out is that the closer they are to 0, the more precise those values are going to be. So let's go ahead and look at the next one. Error propagation. And so I love this paragraph, so that's why I went ahead and put this on your notes. It says physicists and engineers tend to make liberal use of the approximation of delta y by dy. One way this occurs in practice is in the estimation of errors propagated by physical measuring devices. For example, if you let x represent the measured value of a variable, and let x plus delta x represent the exact value, then delta x is the error in measurement. Finally, if the measured value x is used to compute another value f of x, the difference between f of x plus delta x and f of x is the propagated error. And so here's the formula of how to find propagated error. Propagated error is represented with delta y. And that's basically taking the exact value minus the measured value. And that should make sense because you've got what it's supposed to be, its exact value. And if you subtract off at the measured value, you'll see that there's an error there. And so what we're going to do is we're going to go ahead and look at a problem that deals with error propagation. Okay? So if you look at here, it says the radius of a ball bearing is measured to be 0.7 inch, which is in the diagram. If the measurement is correct to within 0.01 inches, estimate the propagated error in the volume of the ball bearing. Okay. So first of all right, I need to go ahead and figure out what I'm given. And I'm given that the radius is 0.7 inches, right? Okay. What is that 0.01?
That's the measurement error.
Measurement error. So,
Data x or trial x.
Well, delta r or dr would work. Now, I could also be a plus or minus 0.01. It doesn't say it has to be above. It's a positive 0.01. It could be a negative 2. It just says it's within that range. And so now the ball bearing is actually in the shape of a what? A sphere. So I know that the volume is 4/3 pi r cubed, right? That's the volume of a sphere. And so now in order to find the propagated error, I need to go ahead and go through the differential process. So I need to find the derivative of this. The derivative of this will be 4 pi r squared dr. Okay? Got to have that derivative with respect to r. And so then now all we have to do is plug our values in. Okay? So if I plug my value in, I get 0.7 squared. And then I'm going to take that times plus or minus 0.01. And when you do that, I want to know, okay, what you get for an answer. Okay, 0.0616, and the label would be inches cubed because you're talking about your error in your volume. Okay, so that's your propagated error. Now just for kicks, okay, we could actually find the relative error if we wanted to. Okay, and to find the relative error, basically what you do to find relative error, you are going to take dV divided by V. So what you would do is actually find your volume with those specific values, and then you would just go ahead and divide the two, and that would give you your relative error. So, okay. The last two things we're going to talk about aren't going to take us very long because they're actually fairly easy. Find the differential. Okay? Differential is defined as dy. So real quick, all I'm going to do now is find dy dx here. What's dy dx in x if it's x squared? 2x. But remember to find the differential. Yep. To find the differential, I'm just going to multiply both sides by dx. So dy equals 2x dx. And there you go. That's your differential. That's all you do. Okay? Let's look at the next one. So first thing I'm going to do dy dx. What will that equal? Just 2 cosine. Yep. So your differential will be 2 cosine x times dx. All right, let's look at the next one. Okay, this one's going to take a little bit of time because what do we have to do?
Just do X, extra X.
You got 2 quantities, so you're going to have to use the product rule. So remember, what's the derivative of x? What's the derivative of cosine? Negative sine. So remember, basically all we do is we multiply along the diagonals. Remember how we did that? So I'm going to take this times this. So I've got negative x sine x. Okay? Plus, along the other diagonal, what do I get? Yep, cosine x. And so then last but not least, now all you need to do is multiply both sides by dx, and that'll be your answer. And that's it. Biggest thing you need to remember here is that you're going to have to use parentheses. Since that's a quantity, you need to make sure you have parentheses around that whole big bunch. And you're going to take that times dx. Yeah, that's good. You're done. Okay. Next one, let's see if we remember our little trick. Little trick, negative 1 over x squared. So my answer will be, yep, negative 1 over x squared times dx. Now some people might write that as negative dx over x squared. You can, but you don't have to. Okay. So, any questions? Alrighty, your assignment then was already on that sheet, but page 240, 7 through 14. Okay, probably not. I'm probably going to add something eventually. So.
Did we skip 3-8?
Yes, we did skip 3-8.